Is it the right meeting?
It should be. Yep, okay. So people are coming back.
Okay. So, yeah, so go and start the slideshow. Okay, now the Windows key and back to Zoom. And now share screen. And there, screen 2. Okay, so you got it? There we go.
We got it.
I don't know where your
Yeah, I don't
share
know why
bar
the
has
controls
gone,
went
but
away, but
it's working, so walk away. Walk
exactly.
away.
No, I have a laser pointer, but I was just gonna.
A physical pointer.
Yardstick. Yardstick would work. And if you're bad.
Thanks, Frank. Okay. All right. Let's just see here. Okay, we've got that. Okay. Oh, right. I'm pretty dim as it is, Liz, so I don't know if you need the light off. Okay, so let's go ahead and try and get through this. So we've had 2 great talks thus far, and I'm not sure this is going to live up to the quality of the last 2. I really enjoyed both of them. But this is a little bit more of the scientific bit, I guess you could call it. My interest in mineralogy is considering minerals as tools to understand geology. I am a geologist first and foremost. Secondarily, I'm a mineralogist. So my goal has always been in my career, both teaching and research, to be able to use minerals to understand environments of formation. To me, that's the ultimate goal. I think that makes me a better geologist. I think it demonstrates the applicability of mineralogy to the broader community, which is really important because as we look across both Canada and the US, we see that there's fewer and fewer people that are actually trained mineralogists. But that's the ultimate goal, is to use minerals to understand geology. From a mineral collecting perspective, if you understand the geology, you also will understand where to find minerals. And that's often how people will do it. They'll look for assemblages, they'll look for key minerals that help them hone in on where places of interest are. So this talk is sort of getting into that. But as I say, I'm not trying to make it too technical, but technical enough that you can see where I'm going with it. So the title of this talk is Alkali Layered Silicates and Chemistry, Mineralogy, and Conditions of Formation with a focus on Mont Saint-Hilaire. And I'm going to use Saint-Hilaire. Am I okay? Everybody can hear me, I guess. Okay, I'm not talking too loud or too soft. We're going up. I love this. This is great. It's like the old television days. So I'm going to be talking about these minerals. And one of the things you need to appreciate right off the bat is, although they sound esoteric, they sound very unique, they're not. These are very much like common silicates, layered silicates that we'll get in any granite or of basalt for that matter. Things like phlogopite and anite that we call the biotite series. So they're very similar. They have some unique differences, and these unique differences really reflect the conditions under which they have formed. I've got 2 examples here. One is the mineral Lalondite, named after the late great Andre Lalonde, a very, very close friend of mine, and I was very proud that I was able to name this mineral after him. And martenite, and that's named after Bob Martin, who used to be the editor of the Canadian Mineralogist. And again, this is kind of fitting because that's what I'm doing now. But actually, Bob was the supervisor for Andre. So it's nice to have these 2. And that's kind of my thinking when I did it, is there was a thought process behind it all. Okay, that's not working. How about we do down? There we go. Okay, mineralogy and rock formation. Cooking au naturel. And I'm not implying that all you're wearing is an apron. But really, that's what geology is. It's cooking. And it's funny to think of it that way because we see the end products. I've got a limestone here. This is, of course, not an igneous rock, but a sedimentary one. But it's the same idea when we're talking about igneous rocks, is that we're really talking about cooking. So I've got a crock pot there that you can keep in mind. So the formation of a mineral. is nature's response to changes in energy.
Yeah.
That's a biggie.
Thank
A
you.
group of chemical constituents or elements, and the prevailing conditions at the time of formation. Those three things. You got to have a change in energy, and now we're moving into the summer season. We're going through a change in energy. We have to have the right elements. If we look at what used to be ice or snow, now it's water. And we have to have prevailing conditions of formation, which includes things like the changes in the oceans, which are now warming our areas. When we look at a rock, we have to think of it as an aggregate of minerals. And this is a big thing, as I mentioned, that George Robinson instilled upon me. You have to look at these as assemblages. You can look at a mineral as an individual component of that assemblage, but the ultimate thinking process should be as an assemblage, a group, because it's all those chemical elements, it's that change in energy and those conditions of formation that collectively give you the minerals that make up a rock. Now, as I say here, they develop and evolve. We think of geology. We think of ourselves. I mean, I look out here and we're getting older. We're all getting older. And that's a reality. That's what happens to us. We think of, when we look at rocks and we look at minerals, we think of them as being something that's been there forever and will continue to be there forever. If there's one thing you can appreciate about geology, you have to think about it as being ephemeral. What you see today will not be there tomorrow. That's the bottom line when it comes to geology. Minerals are part of that, which means that what we see today in a sample from the Ares faunolite or from Varennes or from wherever, it's not going to be there tomorrow in a geological timescale sense. When we have minerals, and this is a really key point about what I'm talking about today, we have primary minerals, minerals that were there originally, and secondary ones. The breakdown and the changes with time has taken those original primary minerals and made the secondary ones. That's part of the cycle. I've got a picture of a sample from Wind Mountain, New Mexico, where I spent some time. The Horvaths came for a couple of days with me there. And we actually worked on a mineral from here that we named Wind Mountainite. But what you see here is a rock. And a rock, to me, when I look at this, I don't just see a rock. I see the minerals and I see the textures that those minerals exhibit. So when we look at this rock, it's a porphyritic rhyolite. So it's a felsic rock. It's got a lot of silicon in it, a lot of aluminum in it, very little in the way of iron and magnesium. And what you see reflecting that are these linear features, which are feldspars. And you can see that the feldspars are all aligned. They have what we call a foliation. Now, who cares? Well, we care because those feldspars are primary, but those feldspars will change with time. And the minerals that I'm talking about today are products of the breakdown of those feldspars. So there is a direct linkage here. Oh, okay. Okay. So let's consider this idea of change, which is really at the heart of geology. On the left-hand side, your right-hand side, sorry, your left-hand side, my right-hand side, we have the rock, the primary rock. And this is a vesicular basalt. And what does that mean? Well, vesicles, holes, that's what you see there. And if you look carefully at it, and I can't even see because I don't have my glasses on, but you can see these green areas in here. Do you know what mineral that is?
Olivine.
Olivine. It's exactly what it is. In fact, it's more than just olivine. That's forsterite, because olivine is a series. It's not an actual unique mineral. It ranges in composition between effectively forsterite, which is magnesium dominant, and phaolite, which is iron dominant. And this will, in fact, not just be an olivine. That will be a forsteritic olivine, so very high magnesium content. Now, when you look at that, you see there's olivine there, and then you can see that there's a number of holes that are in there. Why are the holes there? When this magma that produced this rock was erupting, it actually had a lot of trapped gas in it. And that trapped gas left holes. Effectively, these were bubbles. Now, this is from Kilauea in Hawaii. But when you take this sample, you can't really see much. It looks like a black rock. We call this a mafic rock because it's rich in iron and magnesium and it's dark colored. But when you take that and cut it very thin and look at it under a microscope, you actually can see a new world. And this is part of what I teach. The first course I teach in mineralogy is hand sample identification. The second course is how to look at minerals and how to use an optical microscope to study these minerals. It's a brand new world. It's still mineralogy, different scale, different ways of looking at them. These brightly colored grains in here are all olivines. It's not what I'm interested in. I'm interested in those gray things. And you can see that they have a linear feature or a linear structure to them. These are all plagioclase. And those are actually albite twins. I don't know if you've ever seen albite, but one of the common ways you identify albite, or at least a plagioclase feldspar, is to look for the albite twinning, those linear features. That's what you see in this thin section of that particular rock. Now, the reason that those feldspars are important to the story is because they're rich in sodium, they're rich in calcium, they're rich in aluminum, and they're rich in silicon. All those elements will go to form the minerals that I'm talking about in a few minutes. As evidence of this idea that what began or what was primary has changed, on my right-hand side, my left-hand side, your right-hand side, we'll forget it. This picture right here, it's what we call an amygdaloidal basalt. And if you compare that, if you look at the black areas in that basalt, right in here, and you compare them to these black areas in here at the thin section scale, exactly the same, no difference. But what you see here are materials, minerals that have infilled all those voids over here. That's exactly what's gone on. How does this happen? It happens because geology and geological things are ephemeral. What's happened is that these feldspars that we see in this middle image here have broken down. They've released their elements. And what has happened to those elements? They have recombined to form other elements. In this particular amygdaloidal basalt, we have natrolite. We have another mineral called saponite, which is a clay mineral, belongs to the smectite. Funny enough, a layered silicate. So the idea is that we started with that rock on the right-hand side, and we've ended up with this on the other side through changes. The primary mineralogy has changed, and that's the key. Oh, I can push the button here, can't I? Ooh, there we go. So, just like in cooking, my wife and I are very different when it comes to cooking. She's an excellent cook. I hate her when she cooks. And the reason is she has no recipe. She just does it and it comes out wonderfully. And I've told her that. I told her last week, I said, Juliet, you know, you're a great cook. You really are. You've kept me healthy for many, many years. My mind doesn't work that way. I need a recipe. That's just the way I'm wired. And some people are different. She, when it comes to cooking, can just say, yeah, you put this in, how much? I don't know, just a little bit, you know, whatever. I need to know how much. Is it a quarter of a teaspoon, whatever. But to make a mineral, it's no different. You need a recipe at some level, a recipe. What is that recipe? Well, in a very simple sense, it has three parts. You need the right elements. Okay, that makes sense. That means you need the salt, you need the meat, you need the protein or whatever, and then the vegetable and the starch. You need the right conditions. So I've got a sort of a funny tumbling periodic table over here, and I know you don't want to look at periodic tables, but minerals are chemical entities. You can't understand minerals unless you understand chemistry. And I'm not going to go down that route. I'm not going to go diving into the weeds or anything like that. But you have to think about minerals as chemical entities. That's exactly what they are. You need the right conditions. What do we mean by that? I had a great time this fall in talking to my students in second year mineralogy, because we spent every day almost, we were watching the La Palma, the volcano in the Canary Islands that was erupting. It was fascinating because you had ash flows, you had tephra, you had pyroclastics. This is real-time mineralogy, real-time geology. The right conditions. You need to have something that's melted those constituents in that crock pot. That's exactly what went on the Canary Islands. Then you got to put them together. And this is what I do a lot of. And we're going to talk a little bit about how minerals are assembled, because it's critical to understanding the way they look, their lusters and things like this. So we're going to get into that. I have a student, some of you may know Derek Lung. He's been great. He's hard for me because he keeps me far too busy and I don't have time to do anything else. He's got this passion for what he calls tot blocks. And if you went to Rochester, did he give it this year or last year? I can't remember his talk. Sorry, 2019? Yeah, I can't remember. I actually had him do it this year. He wanted to do as part of one of my labs in optical mineralogy. So he's got these blocks that he uses my 3D printer to print out. It's costing me a fortune in the plastic, whatever, PLA. But anyways, it's great. I support it. Now, what you see here is a bunch of blocks being put together. But what we need to read is we start with something that we are going to call a clinopyroxene. Pyroxene, let's just leave it at a pyroxene. And then we're going to move to an amphibole. And then we're going to move to a layered silicate. These are the atomic arrangements. Nature does not play dice. That's a quote attributed to Einstein, I believe. I'm not sure he really coined it, but whatever, we'll use it that way. There's always a predictability to what we see. And that's another thing you got to keep in mind. Nature is not random. There are reasons for what we see, what we observe in terms of the minerals and the rocks. This is a sequence of mineral formation, and I'm going to talk about this next, or at least in a moment. So let's talk first about the right elements. There's your periodic table. We're talking about alkali layered silicates. So what do we need? We need the right elements. What are those right elements? Well, the elements over here that I have as sodium, potassium in that green box, along with calcium, we need those. And as I mentioned, where are you going to get them from? If we're talking about taking an original primary mineral and producing a secondary one, which are what these layered silicates are, where do they come from? Those elements come from the feldspars. They're key elements in feldspars. What else do we need? We need aluminum and silicon. We need a lot of it. We can even throw in things like boron, which is such an interesting element. Boron is really cool because in most rocks, you never get enough boron. The concentrations are never high enough to produce boron-dominant minerals, or minerals that contain essential boron. You know where it comes from? Ocean sediments. That is the primary source for boron. So it means when we have a mineral that has boron, essential boron in it, there had to be an ocean sediment contribution, which is interesting in our case. But you need those elements. The last group are things like oxygen. Of course, because we're going to make a silicate, you need silicon, you need oxygen. You can also throw into the mix fluorine and sometimes chlorine. Chlorine is not a nice element for a lot of reasons. If I mention Cl2 in First World War, you'll know right away, mustard gas, not nice. Minerals don't like chlorine. And you would look at it and say, well, chlorine is just under fluorine. Same elements, right? They need one more electron, blah, 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 blah. Here is fluorine. Here is chlorine. Here is fluorine. Here is chlorine. Huge. Minerals don't like to take things in that are very different in size. Size matters when it comes to forming minerals. So you can stick in some chlorine. Most minerals don't like it though. Fluorine, yes, because it's very similar in size to oxygen. So you need all of these elements. There's not the entire periodic table. Now, if you're clever, and I'm not saying you're not if you don't recognize this, I have not indicated anything that we call the transition elements.
Correct.
Transition elements are all these things in yellow down here. The reason that these elements can be very important to minerals is because when it comes to color, that's it. They are the primary driving force for color in what we have in most minerals. There's a clue there, because if these minerals that I'm talking about don't involve these transition elements, what color do you think they're going to be?
Colorless.
Colorless, perhaps white. It's exactly what we see. They're all colorless or white. And the reason is because they don't have transition elements in them.
Cool.
Oh yeah, I always get this confused with my students, and probably you may in fact get confused when we use these terms. There's silicon, which is the element. There's silica. So if you have, okay, I'm going to admit in front of all of you, I have a penchant for cigars. And I have a cigar once a month. I'm not addicted to these, but when I get my cigars, they come with these little desiccant packages. That's silica. That's usually, they're using that to suck up the water in the system. So there's silicon, there's silica, and then there's a silica tetrahedra. Okay, we're going to talk about this in a minute. Again, complicated. They each have a different meaning. That's my point. Okay, so when it comes to elements, where do they come from? Where, even at the primary source, are they coming from? We have to think about the part of the earth that we can get to. The most easily accessible part of our planet is the crust. And the crust is no more than the skin on the planet. It's the reality of it. But that means that the elements that we're going to be talking about and looking at in these minerals have to somehow involve the crust. We can't get to the mantle. That's a reality. You know, you might have seen, what was that crazy movie a few years ago? Journey to this. No, there was a newer one though. Yeah, there's a newer one. I can't remember. Yeah, I know the exact. Oh, I understand what you're saying. So I guess we're dating each other. But there's another one, and they talk about going to the mantle. Forget it. We're never getting to the mantle. We're never. But we can look at ways. But that means we have to appreciate what goes on in the crust chemically. And if you look at the Earth's crust, there's really two elements. Almost 70% of the Earth's crust is made up of silicon and oxygen. Who cares? Well, that means that most of the minerals that we see at the surface are going to be dominated by silicon and oxygen. That's the reality. Now, we also have a few other bits, fluff, if you will. This the stuff that really makes life interesting. But we have things like calcium at about 4%, sodium at about 3%, potassium at about 3%. That's interesting because the minerals that I'm talking about, they're forming from feldspars. Well, what elements dominate feldspars? Silicon, aluminum, calcium, sodium, potassium. Why? Because the Earth's crust is really rich in those particular elements. Okay. So you need key mineral or the key mineral hosts to these minerals, to these elements. Plagioclase feldspars. It's where it's at in this particular talk. But we also have mafic minerals. Do you know what I mean by mafic?
Lots of amazing iron.
No, I don't think everybody does, and there's nothing wrong with that. Mafic means rich in iron and magnesium. So the olivine that we looked at a few minutes ago in that basalt, that's a mafic mineral. Plagioclase is what we call a felsic mineral because it's rich in aluminum and silicon. So we have these two broad groups of minerals, mafic minerals and felsic minerals. Now, in addition to everything that's going on here, these minerals are anhydrous. Do you know what that term means? No water. Waterless. Water, as I was talking to Pete the other day, I guess yesterday, sort of my hours and time are all mixed up. We were talking because he did groundwater and water analyses, water work. And we were talking about dissolution. Was it you I was talking to? Yeah. And water is the universal solvent, right? It dissolves everything. There's nothing that water will not dissolve. So you need to have minerals that start life as anhydrous because that means they have no water in them. As soon as you introduce water to them, they start to break down. That water actually starts to etch them and dissolve them. So you need that. And you need a source of water. Well, we look at the surface of the planet, 70% of the planet is covered in oceans. There's lots and lots of water. Well, yeah, but that's at the very near surface. We're talking about in the crust. And in the crust, there's not that much water. When you get into the mantle, I don't know if you remember a few years ago, they were talking about oceans of water that they found in the mantle. This was one of the hot things. There was no liquid water. They had trace amounts of water in some olivine because olivine is volumetrically huge. It was like there's seas. No, it's nothing like that. Water doesn't like to go into most minerals. And part of that is because of the dissolution properties of water. You start putting it in there, they fall apart. So when you need water to make the minerals I'm talking about, you need that water also to cause the breakdown of those feldspars, those initial feldspars. Water is what we say is incompatible. So my wife and I are somewhat compatible, I would say. Tracy and Frank are very compatible. Yes, you are. So the idea, when I say incompatible, what I'm really saying is minerals don't, they and minerals don't like each other. And that's important because it means only at the latest stages of crystallization, after all the minerals are formed, do you get elevated concentrations of water. Otherwise, it's very weakly and very minorly distributed. So importantly, water increases with time. As Las Palmas that I showed you there, where the volcano was erupting, that would have had some water in it. And as that's crystallizing, the water content of the magma actually builds up. That's why you actually get the explosiveness, because the water builds up to a critical point and then boom. I'm trying to go fast. So, Bowen. Anyone ever heard of him?
Yes.
He was a Brit. Did you know that, Quintin? He was a Brit. Yeah, he was British by birth, who came to Canada. And he is one of these unsung heroes because he came up with what I call an elegant explanation for crystallization. To me, you know, I got my pointy hat on here and I can get as complicated and technical as you want. The process of crystallization, when I say something is elegant, I should preface this. When I say something is elegant, it's simple and accurate. I love elegance because, and I teach my students about Bowen's reaction series. He was a Canadian born abroad, and he published the first ideas on the crystallization of magmas. That's important. It matters for our talk because you probably have seen Bowen's reaction series before. Have you seen this before?
Yeah.
I don't know if you really know what it means. It's a very elegant explanation as to what goes on. On one side, we have what's called the discontinuous series. We call it discontinuous because there are gradual changes, but with each change, it's a new mineral. You start with olivine, just like those green crystals, those phenocrysts that we saw in the salt earlier. They will convert with time to pyroxenes. Pyroxenes will convert with time to amphibols. Amphibols, key, will convert with time to layered silicates. That's important because what we're talking about here are layered silicates. This gives us a context of where these minerals that I'm talking about would have formed in the whole process. They're not early, they're not mid, they're late. That's important. The reason that they're late is because as these early minerals, I'm pointing here and you people can't see me, as these early minerals have formed, they have relatively little silica, SiO2 in them. As the minerals form, the silica content goes up and it goes up. And that's what drives the changes that you see there. And I can put it on the board and show you. That's all of it. Mg2SiO4. The next mineral to form here would be a mineral called enstatite, which is a pyroxene. And just as a general sense of what's going on here, you can see that the ratio of magnesium to silicon, 2:1. What that means is every time an olivine crystal forms, it's taking out more magnesium than it is silicon. And when that happens, that means whatever is left over gets elevated or enriched in silicon. Here, the ratio is 1:1. So now we're taking that.
That's now the second spider.
Maybe somebody up unhappy with me writing on the board. Yeah, I get it. Okay, so the point is get silicon to the right concentration to make a layered silicate. It's not early, it's not mid, it's towards the latter parts of the crystallization process. Now, the other branch here is what we call the continuous branch, because that's effectively one mineral. It's plagioclase. The initial plagioclase will be very calcium and aluminum rich. And as it grows with time, it becomes more sodium and silicon rich. And that's because the silicon contents increase. But there are other things that go on here that I've kind of indicated as changes as crystallization. So this is hot, hot, hot. That's what the red means there. And blue means cool, cool, cool. Crystallization. So silica increases, alkalis increase, water increase. That's important. To understand mineral formation, you have to understand Bowen's reaction series. Very elegant because it's simple, but it actually answers many questions. Not perfect, but it still answers many questions. So the right atomic, the right atomic, what did I write here? The right atomic arrangements, that's right, sorry. So you need to have these things. So we've got the right elements, we've got the right conditions. Now we got to have the right arrangements to take in these minerals. And this comes into an appreciation for how atoms are joined together to create minerals. It's really important because it really is at the heart of what I'm talking about. Here I have a phlogopite, and I don't know what that is. It's maybe ½ an inch or something like that in length in a lampropherdite from Ontario, northwestern Ontario. This is the mineral. This is phlogopite. And phlogopite is a layered silicate. It's got magnesium and silicon in it. And this is what it looks like. And you've probably seen these diagrams before. And it's like, okay, there's a bunch of colored things and there's lines to them. But what do they really mean? When I look at them, I see them as arrangements, which is really that arrangement that you see here is exactly what goes on at the atomic level here. But more importantly, it shows a couple of key things. You see this TOT, tot. Remember the tot blocks that I mentioned a few minutes ago? That's where Derek stole the idea from. That's where he got it from. T stands for tetrahedral, and I'm going to mention this, what this is. O stands for octahedral, and T, again, is tetrahedral. And then in the middle here, you have what are called interlayer cations. Now, it doesn't matter what really goes on here. The thing is, these things are layered. So when you think of a mica and you want to identify a mica, what's one of the first things that comes to mind when you're trying to identify a mica? Cleavage.
Cleavage.
Got that perfect basal cleavage. We call it the 001 cleavage. You know, when I introduce muscovite to my students, of course, everybody takes the books like you're supposed to do, and you know, they rip them all apart. Perfect cleavage. Why does that happen? It happens because of this. So what happens is you effectively have what I call the Oreo. This is an Oreo. You know an Oreo cookie where you have the cream in the middle and the two chocolate cookies or whatever those biscuit parts are? That's what the T's are. The T's are the biscuits. And then in the middle there, you have the cream or whatever that stuff that I'm not supposed to eat is anymore. But you have. Between them, you have these things called interlayer cations. So when you rip or you cleave a mica, what you're really doing is you're breaking the bonds here. These bonds, usually it's potassium, they're big ions and the bonds are very weak. And so what happens is you actually break apart the Oreo parts. This Oreo part stays, and this Oreo part stays, but they become separated from one another. They're no longer held in together. I like to think of it almost like the interlayers are like my hands. So, you know, if I should be having that cookie, so I get wrapped on the hand with it, right? So the interlayer cations are like my hands. So I take my hands away, the cookie is still there, but it's no longer joined to the other parts of the cookie. You follow that? That's important. So these structures are important in that respect because they influence the properties that we see. If you have questions or don't understand something, just shout out. Yep. No, because this can all be in the case. Sorry, you're right. With phlogopite, yes. This is because in this O region here, that's going to be magnesium, and magnesium is a mafic element. That's in that sense, yes. So that you can think of it as being felsic, mafic, felsic. That's right. That's right. When you look at them, now you're never going to see this. I've never seen the structure of a mineral. I can draw them up on all my software. It's fine. I can do that. But I see the effects of it. And one of the obvious effects you see in mica is the cleavage. And the cleavage is there because these sandwiches, the Oreos, are really tightly held. But between them, it's my weak hands. And my weak hands, I like the cookies, but I get slapped if I have too many of them. So they break. They break. And that's exactly what happens when you break off or cleave a piece of phlogopite. It's going to become important. So whether you understand that, it's okay. It's not a problem if you don't, but appreciate that when you're breaking something, it has physical meaning. You're breaking chemical bonds, and the chemical bonds you're breaking involve these interlayer cations. Super weak, like me today, because I'm kind of tired. They stay with one part. They stay with one part. There's no, only with one. So what happens here is that this will break off, and that potassium or these yellow things here, they'll stay with this bit, but they're no longer joining the two Oreo cookies together. I don't know if they split apart. But you bring up, I mean, one of the most important groups of minerals that we have on the planet. And we'll talk about, like I work on sulfides and I work on platinum group minerals, and people, or gold, I work on gold, a lot of work on gold. People will say, oh, those are the most important minerals because they bring wealth. Well, the real basis for wealth and survival on this planet is soils. Try living a day without food. It's pretty hard to do. Even though I try, I can't do it very well, which means that you need to have fertile soils. And what are fertile soils composed of? But altered. So your question is, Steve, is that your name, Steve? Yeah, Steve is right on. What happens is, this is where you get alteration. So when you look at the quality of a soil, you're really talking about how much of that potassium is left. When you break it down or alter it too much, it goes, and the fertility of the soil will also go down. We have a group of minerals that we call clay minerals. That's what clay minerals are. Exactly the same. They're all layered silicates. Okay, so let me see what I see here. Alkali layered silicates, arrangements of atoms. All right, so an example, gyrolite. Now, gyrolite, you might think of as being a zeolite in many ways, because it typically will form as a secondary or late stage mineral in basalts, just like that amygdaloidal basalt I showed you earlier. That's what you would think of. It's a member of the alkali layered silicates. Very interesting. It's not a zeolite at all. And so what are the essential components? Well, if you have a layered silicate, like gyrolite, you need to have layers of silica tetrahedra. Now, the layers that we have in these minerals I'm talking about are not exactly like those in things like phlogopite or biotite. They're a little bit different. And the differences actually have or manifest themselves in very unique properties. So on this side here, I have what is a silicon tetrahedron. And that's just silicon joined to 4 oxygens. We call the shape around that a tetrahedron. It looks like, how are we doing for time? We're good? Okay. It looks like a pyramid of Giza, or the Giza pyramid. That's what it looks like. And it just means that you have oxygen bonded or joined to silicon. And that shape or the form, we call a tetrahedron. You might get that in chalcopyrite. If you've ever seen natural chalcopyrite crystals, they typically will form in tetrahedra or pseudotetrahedra. Quite honest. But when you look at the structure of some of these layered silicates, like the mineral martenite, so how is it different than what you get in phlogopite? What you see here, these blue things are boron, not silicon, they're boron, but they're playing the same role as silicon is. And you get a sheet. You get a sheet of tetrahedra. What's different is you see the blue, which are boron, they point up. You see that? You see the apices, the tips, if you will, of the pyramids, they're pointing up. The silica tetrahedra, to which they're joined, point down. This is very different, fundamentally different. This is what the tetrahedra look like in phlogopite. They're all down, all of them. That's very, very different. And this manifests itself in something that you see right here. When you look at these, how would you describe the morphology of these crystals? What would you call them? Spherical, right? And if you looked at them as a sphere and took that apart, in other words, look at the components of that sphere, how would you describe it? They're plating. So what you've got is a series of plates that have arranged themselves to form a sphere. Why does it do that? Minerals like phlogopite, I would really be struggling to, maybe I've seen a couple of examples of spherical phlogopite, maybe. Certainly not very common. So what's the dealio? If they all have the same structures, then how come they're not all forming spheres? Well, the reason is in part because the way the silica tetrahedra are oriented make them much more deformable. And that leads to plates, but the plates actually start to, as they continue to grow, they kind of grow inside or into the one another. Now, the other thing is, what do you notice about those red tetrahedra here? What do you notice about that? They're rings. There are 6-membered rings, and they have a particular form or symmetry, do they not? What would you say? Star of David, yes. That's true, but how would you describe the symmetry of that? Hexagonal.
Hexagonal, sure.
What do most micas look like? If you've got a perfect crystal of a mica, what does it look like?
Hexagonal.
There's why. Now they aren't, and the reason is because they're like steps on a stair steps where they're offset, and that's why they actually drop down. But if you took one single layer of these things, they'd be hexagonal, and that is reflected in the crystal, the gross crystal morphology. We often see them as hexagons, and you think, oh, it's hexagonal. I was just looking at a willemite with Bill this morning, and I wasn't sure of the symmetry of willemite. I looked it up. It's trigonal, and that's exactly what I was seeing, something consistent with that. So the symmetry will come from this. It may differ because of the way the layers are offset, but the basic appearance will look hexagonal. Do you remember that little martenite crystal I showed you at the very beginning? It was a nice, looked like a hexagonal plate. How come it looks like that? Because the silica tetrahedra are joined into these six-membered hexagonal length rings. That's why. So those details manifest or grow themselves to make a crystal. And then we see that evidence.
What are you trying to represent in terms of the boron? Is it all those borons?
Yep, they connect. Yep.
All oriented differently.
Correct.
Appear to be tilted if I'm looking at.
The difference here, and this is what's common to all the alkali silicates. On this side here, this side here, you can see that all the tetrahedra are pointing down. They're all in the same direction. Here, some of them, most of them are pointing down, but some of them are pointing up. That's a characteristic of all the alkali layered silicates. They have these basic rings that are joined together. Doesn't have to be boron. It could be silicon, it could be aluminum. But the difference is, or the similarity is, that all these joining tetrahedra point up. And that in part relates to how the crystals grow and the morphology they adopt. That make sense to you?
You know, I see what you're saying. That because they're all pointing up, they've got to, they are the adapting.
That's right. That's right. That's right. That's right. That's right. That's good. That's very good. All right, let's continue on here. I'm probably over time already.
Nice to know. The question, the blue boron things, they're not boron atoms, they're actually boron with oxygen.
Just like here, except in the center, instead of silicon, it's boron.
They're physically different size.
Yes, they are, because boron is a different size than silicon is. Yes. But the interesting thing here too, like I mentioned, in most rocks, you cannot get, it's impossible to get enough boron in most rocks to make a mineral that has, you cannot make martenite without boron. It has to be there. That's part of its chemistry. And you can't do it with most magmas. You need ocean sediments. And why? It's so interesting. Because these things, remember I mentioned clay minerals? They have these huge surface areas, and things like boron, at the top here, there's nothing joining to them. That's where boron gets stuck. So they become sinks for boron. That's why you get it in oceanic sediments. And it's not just any sediment, it's the clays in the oceanic sediments that actually trap the boron. So martenite at Mont Saint-Hilaire had to have had an oceanic component in its formation. 100%. 100%. And that's mind-blowing. To me, that's mind-blowing. We know that there were shallow seas in the Silurian Ordovician at the time when Saint-Hilaire was being emplaced, but we don't think of that effect. That's an effect right there. There's no way. Tourmaline anywhere on the planet. You got tourmaline? Everybody knows tourmaline, dravite, schorl, ilbite, whatever. You have to have a source of boron, and it will always be some kind of oceanic material, always, because that's the only place you get enough boron to make boron minerals. Okay, so I think we're okay on the differences in the tetrahedron. They all point in the same direction in most common micas, like phlogopite and anite, or generally biotite, muscovite. They go up and down in the alkali layered silicates I'm talking about. Okay, come on. Okay, it's not playing now. It's not, what do I have to do?
There's your cursor.
Yeah, I can't get out of the box.
Go to the corner.
There we go. Okay. So we need the other component. So we talked about the tetrahedral layers. The other component is what we call the octahedral layer, that O. Remember the TOT Oreo? Remember that O? this is a big difference too. So what I have here are things that are called octahedra. And you're familiar, for example, with octahedra of fluorite, for example. You were talking about, I think, some of the Illinois material, or I forget what you were talking about. No. I'm pointing to Pete Richards. Because you were talking about downsizing, but you were going to hold on to your fluorides. Illinois, right? So you're familiar with what an octahedron looks like. Well, when we talk about an octahedral coordinated cation, we're talking about something where you have a cation in the middle, you have oxygens around it, and the form that takes on is an octahedron. That's what we mean by it. And we can form sheets of these octahedra. And here's one from martenite, and here's one from phlogopite. And they look very similar. They're all octahedra. You can see the triangular face that exists right there. That's the triangular face right there. So we're looking at octahedra that are tilted. But it's a sheet of these things. Now, in phlogopite, all of these octahedra are magnesium. Okay? In martenite and in all the alkali silicates, all of these are sodium and calcium. Sometimes some potassium, but in general, all sodium and calcium. What's the dealio there? Who cares? Remember I told you fluorine, chlorine? Okay. Magnesium and iron, sodium and calcium. Magnesium and iron, sodium. I don't know if you guys can see me. Sodium and calcium, huge. This does something. It strains the structure. But importantly, where those elements are is in this layer. And I know Bill Lechner will ask me a question. I'm finding a toonie. I was going to get a $5 bill out, but I think that's too valuable. Okay, I got a toonie. He's going to ask me, Ellingsenite from Eris. I've got some weird chemistry that doesn't fit for Ellingsenite. That's a question he was going to ask me. I've beaten him to it. Because what makes this layer of octahedra so interesting is that you can have anything in there. In other words, you can have sodium and calcium, but you can have various ratios of those elements. So when you talk about Ellingsenite, which I almost fundamentally don't believe is a valid species, there's a lot of reasons for that, but I'm not going to put on my pointy hat, do techno speak or anything like that. Whatever you have in here will have sodium and potassium, sodium and calcium in it, but you can change the ratio of sodium to calcium. And that's what Bill would have asked me about. How come I'm getting these weird ratios and they still call it Ellingsenite? It's because you can have very highly variable sodium to calcium ratios in this octahedral layer. Okay, so in phlogopite, you have magnesium, easy to work with, sodium and calcium in the alkali layered silicates.
Retrograde.
Okay, so what else do you need? Water, lots of it, lots of it. One of the key characteristics of these minerals, I could have called them alkali layered silicate hydrates because they all have water and not a little bit of water. They have lots of water. And this is also important because these minerals can undergo color changes. And I fundamentally believe that it's the loss of water, maybe even in some cases the gain of water, but mostly the loss of water, which influences the colors that we see. Some of the mineral that I will talk about, kodamaite, began life as being almost an emerald green color. And after a few months, it turned yellow. Sometimes they're just white. And I think a lot of that has to do with the water. These minerals have a lot of water in them, which also makes studying them very challenging. And I've got a couple of examples. I've got another one here of that Ellingsenite. And okay, let's continue on. You need lots and lots of water. So put it all together. What I've got here are minerals, an example of the mineral martenite, which is an alkali layered silicate. So if we put that, we join everything together. We join the tetrahedral layer to the octahedral layer and add in water. What does it look like? And how does it compare to more common micas?
Pretty similar.
They look exactly the same. So when I have a tetrahedral layer here, remember that boron and silicon layer that we were just chatting with Liz? There it is. That's exactly the same layer that we get in flocopite, except in flocopite, it's just silicon and all the tetrahedral point down. Then we have an octahedral layer. Here in martenite, as in all of the alkali layered silicates, we have sodium and sodium and calcium. What do we have in a flocopite? Mainly magnesium, but some iron, some of those mafic elements. Alkalis, mafic elements. And then we have our TOT. Exactly.
Is that what distinguishes microgroup minerals from other layered silicates? Is that all technically you're pointing down in
Yes,
microgroup?
yes, they're all like that. They're all like that. Yep. And then in that interlayer space, instead of potassium that we would have in a muscovite, okay, a muscovite is potassium, flocopite potassium. That's where it goes. So that's like I was saying with my hands, and you're tearing these things apart. Here, right away, water, man, water, the bonds made with water are super weak. I mean, I'm sure if Frank and I had an arm wrestle, I'd lose big time. And that would be an example of that. He's much stronger than I am. Look at those. Look at those biceps. The guns. Look at the guns on him. The point is that this is going to manifest itself in a property. Not only is it going to be a good cleavage, it's going to be a super good cleavage. Super good. Why? Because the bonds made with water are super weak. I'm the weakie. He's the strongy. He's the potassium. I'm the water. I lose. It's the same idea. But structurally, they're exactly the same. There's no difference. TOT with interlayer. That's what it is. So here it is. You all wanted to hear about the alkali silicates. Well, I put together a chart, and it's not even comprehensive. It continues to go on. Some of the minerals are going to be extremely rare, and you've never heard of them. Federite, it's kind of a rare mineral. Lalondite I've mentioned, and martenite I've mentioned. Cairncrossite. I don't know if you know Bruce Cairncross. Very, he's a. Yeah, I'm just trying to think. Is it Johannesburg? I think maybe Johannesburg. In fact, we just tried to get him as an associate editor, and he considered himself not a mineralogist. He's a gemologist. He doesn't know anything about minerals. And I said, what? Anyways, Bruce Cairncross, mineral named after him. Kodamaite, which I'm going to make a few comments on. Ellingsonite. I could have put that in air quotes because I'm not so sure about that one. I think that one is, I don't think so. Rhyolite. And in fact, the whole group is named the Rhyolite group. Okay, I've taken a little bit of liberty here. I'm probably going to get my hand slapped by IMA, but I got big shoulders. Frank has made a point of that. So point is that this is the Rhyolite group. The whole alkali layered silicate assemblage, we call it the Rhyolite group. We have gyrolite that fits in there, and truscotite, and tungusite, and minehillite, and orlimanite. So nice names. I think this list is extremely underrepresented. I think there are many, many, many more to be found, particularly because, just as I mentioned, I've taken my $2, my toonie off there, just talking about Bruce and what goes on in that octahedral layer with sodium and calcium. There's a whole pile of variability that's possible there. But this is it. And I've described the Londite and martenite, and now I'm in the process of describing Kodamaite. And I think there's more than one Kodamaite at St. Hilaire. We used to call this UK 77 for those that are MSH aficionados, UK 77, and there's UK 77A, UK 77B, UK 77C. So there's a whole series of these things.
Is sabinite in that?
Nope, because sabinite is a carbonate. So it's not a, and it also has zirconium in it, zirconium and titanium in it.
Frascatite.
It's layered for sure. Okay, continue on. All right. So where do you find them? Highly alkaline environments. What does that mean? Lots of sodium, lots of calcium. You got to have those elements. That's what I started talking about with the crock pot. You need those elements. The primary elements, and I've made some comments here, MSH and Eris and Poucas de Caldas in Brazil, very famous location there, and Kola Peninsula, of course. But anytime you have an alkali basalt, remember I showed you those basalts at the very beginning, the vesicular and the amygdaloidal? Well, those are alkali basalts. They can form these minerals as well. We think, oh man, this is only occurring in these very hyperalkaline, silicon undersaturated environments like we have at St. Hilaire or at Eris. No, no, no. Anytime you have the right elements, the alkalis, the right amount of silicon according to Bowen's reaction series, and lots of water, you can make these minerals. So basalts can form them just as easily.
Hmm.
The primary environments must be altered. You can't deal with a primary environment that hasn't been altered. Alteration is critical because it takes those feldspars and releases the elements. They can then subsequently recombine to make the minerals I'm talking about here. And you need vugs. Now, the vugs themselves are essential not because of the fact that they create space for things to grow in. Last night we were sitting with Jonathan and Robin, and Jonathan mentioned that, oh, something's wrong with your leg. What's that on your leg? And with my veins popping up, I guess I was excited or something at that point. It's a conduit. What vesicles do, vugs, is they create conduits through which water can migrate. So if you have an impermeable surface without vugs, you're not going to have the conduits, the veins, the arteries through which water can percolate. You need the water, but the water's got to be able to get at those primary feldspars. And so at St. Hilaire, where we have these right environments, include the marble xenoliths. So these are blocks, and I've done quite a bit of work on these particular things. We never knew exactly what they are until, again, we were talking to Pete yesterday, talking about the brachiopods that were infilled with pectolite and ribachite, which is a sodic amphibole, which was part of the story in proving that these marble blocks here, they actually were at the top of St. Hilaire and fell into the magma. We look at St. Hilaire today, if you've ever been there, or if you've ever seen the Monterey Hills, these are high hills. They weren't always like that. Geology is ephemeral. They were actually intrusive rocks. They never made it to the surface. The intrusion that we call St. Hilaire, it never made it to the surface. It was below the surface. And so what we're looking at with these marble xenoliths is material that fell into the magma from above. That's what exactly happened. And we also get it in what we call the sodalitites. It never has rolled off my tongue. Do you know what a sodalitite is? I'm not even really sure myself.
A rock that is
rich in sodalite, the mineral sodalite. And if you've ever had UV and looked at hackmanite, you can see the fluorescence. I still call them sodalite cyanide xenoliths, but they're part of the whole environment.
Garnetite is the same.
I'm sorry?
Garnetite is the same.
Garnetite. Okay, yeah, metamorphic. Okay. So I've got an example, and here the Lalondite was actually found in association with one of the marble xenoliths. So these are blocks of carbonate that fell in, but they're rich in calcium, and they interacted with fluids that were rich in sodium and calcium as well. And then I have kodamaite here, and kodamaite, you can see that it's growing on a eudialyte crystal. Okay? So in these sodalitites, you have some eudialyte as well. Okay, all right. Okay, so I can identify these minerals. Can you? And I think any talk or any presentation, you'll take whatever you take away from this. You probably say, I wish I had my lunch or something like that. But what do you take away from it? Well, how do you know how to identify an alkali layered silicate? I call it tricks of the trade. It's stuff I've learned.
Yeah.
Not always I've learned it myself. Somebody's told me it or something. But there are a number of features. Look, I go up to 7 here. So first of all, generally colorless to white. It's very, very common that these minerals lack color. Why is that? Because they have very little in the way of transition elements, very little iron and magnesium, things that would normally color them. They occur in platy or bladed crystals. And I've got an example here. This was provided by Elsie Horvath through Les Horvath. And you can see the blades. This is kodamaite. That's what it looks like under an SCM. And that scale bar there that you can see is 100 microns. How big is 100 microns? See this? That's a hair. I still have some on my head. Each hair, on average, is 100 microns. So that's how big 100 micron, if you're ever wondering how big 100 microns is, that's a great way to do it. So you can see that they're actually somewhat bladed. So they don't look like super hexagonal plates, but they have a platy morphology. Ellingsonite here, Cairncrossite. I've got Ryerite, which is from the Isle of Skye, and of course Martinite right here, which is reflecting that hexagonal morphology that I was talking about. They all have a perfect basal cleavage. How come? That water in the interlayer, it's so weak, it doesn't hold them together. It's like gone. They fall apart. They break apart, but they break apart in sheets. They have a low Mohs hardness. They're super soft. How soft? Probably 2 to 3. Much softer than if you were to estimate the hardness of a phlogopite or an anode or something like that. They have a pearly luster. Pearly luster, what does that mean? Well, it looks like a pearl. That means something. It relates to the refractive indices. And that is the ability for, if you want to think of it, of material to bend light. You always, as in a high school, you did those experiments where you put a pencil in water and you see it bend. That's refractive, the change in refractive index. These all have a pearly luster because they are dominated by light elements. Sodium, calcium, aluminum, and silicon. These are very, very light elements. So they don't significantly affect or produce high refractive indices. I was looking at one of Robin's samples this morning and I looked at it and immediately what stuck out was this material I was looking at, which was not the mineral I was supposed to be looking at, had a very high luster. It was ansilite. And if you know ansilite, one of the key characteristics of ansilite, yeah, sure, you get these pinkish or mauve dipyramids, but it has a high luster. And it has a high luster because of the rare earths that are in there. They really distort the light, bend the light, if you will. Individual plates are generally flexible. So you can, how you can take a crystal of muscovite and you can bend it. And eventually you reach a point of no return, you break it. Oh, it's like we get another one, whatever. These ones are super flexible. You can really flex them, much more easily than you can with a phlogopite. They may exhibit a UV response. And this is something that I don't quite understand, but I think I know why they potentially show a UV response. And a UV response can be dependent on chemistry. It can also be dependent on defects in the structure. But importantly, you don't want iron. Any minerals that will contain iron are not good for a UV response. And the reason is because UV depresses the UV response. It's like the downer, if you will, when it comes to UV. So I think the reason that many of these exhibit a UV response is because they have very, very little in the way of iron. High iron is not good for UV. So there are other things because the ultimate cause of that UV response is still has to be explained. But certainly the lack of iron, that's a good thing.
Are they also elastic, like and elastic?
Much less so than you would think of with a muscovite or any kind of biotite, because they, in other words, they flex, but you reach that point of no return much easier. Yeah, that's right. That's right. I'm interested in minerals because they tell me something about the environment of formation. Studying a new species, that's great. And I know as mineral collectors, one of your dreams, let's be honest, is to find a new species. It is. Why not? Because then you've discovered something that somebody has not seen before. To me, that is only the beginning of the journey. Because understanding what a mineral is, as I started at the beginning, a rock is composed of minerals. You understand the minerals, then you have an opportunity to understand the conditions under which the rock formed. So, what the heck with alkali layered silicates? What are the conditions under which these form? You know what? Fascinating. And the more I learn, the more I know very, very little. Because I'm discovering and working on new minerals. People, my engineering friends, they've done this. It's been done. Whether you work on silicates, whether you work on platinum group minerals, whether you work on sulfides, engineers have already done it. Because they sit there and they do their shake and bake science. That's what they do. So they're playing around with this. I'm not a concrete expert. I don't like concrete. Concrete's very difficult to understand. If you've ever worked on concrete and tried to understand its chemical makeup and the minerals that form, because they are minerals that form, very, very complex. But when it comes to alkali layered silicates, my engineering buds, they've already done it because these form in cements, which is fascinating to me because then I've got an idea of the conditions. They're growing them, right? They're making them. Then I can extrapolate that to use that to understand the conditions in a rock. Right off the bat, I've circled in red there, gyrolite.
Yeah.
Okay, we've talked about gyrolite. We see these balls, there are plates that are forming in balls. What do we know about gyrolite? See that number there? I don't know, Frank is close, I suppose. Maybe on the screen. Can you see what that number is? 100. And that is in degrees Celsius. So that's not high temperature.
No.
In fact, if you really look at it, you're talking about 90 degrees Celsius. They're forming gyrolite, which is an alkali layered silicate, at 90 degrees Celsius. That's not hot temperature. It's not very hot at all. Very cold, as a matter of fact, which then lends itself to understanding when we see an alkali layered silicate like martenite or gyrolite or orlimanite. We're talking about things that are forming at very low temperature, not magmatic temperatures, not 12 or 1400 degrees Celsius, a few hundred degrees at most, very low temperature. In fact, what they've done is plot up minerals. Truscotite, we talked about truscotite. That was one of the ones I put on my, my table there, right? And gyrolite. So what's really going on here? You can see I've got an ellipse here. And down here you have this thing. It's a calcium hydrogen silicate thing, not a mineral. Then we have the Z phase or Z phase, not a mineral. And then we get gyrolite, and then we get truscotite. And if we get really high enough in temperature, and that's 1000 degrees or 900 degrees, we get calcium silicate. And what's calcium silicate more commonly known as?
Awesome.
Well, Wollastonite. I pointed to Pete. I thought it was his big moment. It's okay. I still consider you a friend.
Reminds me of the Riverside Quarry
Yep.
crest
Yep.
mark.
Yep, that's right. That's a nice high-grade contact metamorphic environment. Yep, and you'll get these kinds of minerals. But what really matters to these minerals is what I've shown here on the my right-hand side. So this diagram right here, and you can see you go from this amorphous gel. That's the first thing to form. It's not a mineral. It doesn't have an arrangement, atomic arrangement, at least a periodic one. Then it gets a little bit more organized, and then a little bit more organized. And what I mean by that is, remember we saw the TOT, those groupings? They start to figure themselves out. That's what's really going on. And so this process is something that we call ordering. That involves time. It needs, minerals will often form from these initial gels. And what a gel is it's got water in it, it's got alkalis in it, it's got silica in it. It's just a mess, and it's got no internal arrangement. But with time, things start to, because of the change in energy, they start to arrange themselves appropriately, and you get minerals ultimately forming. One of the other problems in studying these layered silicates, these alkali layered silicates, is because a lot of them are in this region right here.
That phase. Yes.
They're between being ordered, a mineral, and not. They're in that twilight zone. So it takes time. So sometimes you can look at specimens and they'll be very well crystallized. By that, I mean, if I look at them with x-rays, they scatter x-rays very nicely. They might look like they're nice crystals, but they still internally are not arranged. But a lot of them are in this gray area right in here, this sort of what I call twilight zone. With enough time, they will order themselves and create the minerals that we're used to talking about, at least in this talk. Okay, so just as a summary, 12:20, I think I'm over. Okay, summary, right elements. If we're talking about alkali layered silicates, we need alkalis, we need silicon and aluminum, and the last one, water, lots of water, lots of water. You need the right atomic arrangements. TOT, the Oreo package, the Oreo cookie, and then things in between. In the case of these minerals, because they have so much water, it's the water that fills in the gaps, if you will, between the Oreo cookies, the TOT. You need the right geological environment. You need something that's highly alkaline. It doesn't have to be a cyanite like at Eris or at Pocos de Caldas or at Mont Saint-Hilaire. It could be an alkali basalt. You need something that's very, very rich in alkalis. That's the key. And with abundant feldspar. And right here, what I've shown you is a way that I look at minerals. And I've got 3 images here. They're low quality and they're not so good, but they illustrate the way I see minerals. This is what you as many collectors would be bringing to me. You'd be looking at this and saying, I got these yellowish balls. This stuff started as green actually, but I got these yellowish balls. I have no idea what they are. I put acid on them. They don't effervesce. You know, I put a UV source on them and I'm getting something. So then you'll bring it to me and I'll have a look at it and say, I don't know what the heck it is, but maybe it's an alkali layered silicate. So I'll look at it in a little more detail, usually with a scanning electron microscope where I get chemistry and sometimes I'll get morphology. And here, for example, right away, I see it's got a layered structure. It's related, but it's layered. Then I'll take that to the next step which is to understand how all the atoms are put together. Because once I've done that, then I've nailed it. I know exactly what the elements are. I know how they're arranged. And that's really the ultimate goal. So, and I think that's all, folks.
Excellent, excellent, very good.
I noticed that Bill was quick off the mark there with his hand up. I guess he wants his toonie.
Just a very quick question.
Sure.
The water molecules that hold the layers, yeah, you say that the bonding is
Very weak. They are hydrogen bonds. Absolutely would be accurate. And they're very weak. Hydrogen bonds, you know, when I'm teaching minerals or mineralogy, we talk about the three basic types of bonds, which are ionic and covalent and metallic bonds. But when you get into these kinds of environments where there's lots of water, hydrogen bonds are so important because they are the extra fluff. I wouldn't even call them crazy glue. I don't know what I call it, like that old brown glue we used to use. It's like it's there, it has some tackiness to it. But yes, it's hydrogen bonds that holds those layers.
Are you familiar with the evaporite deposits in southeastern Israel?
I can't. Yeah, there's a question. Maybe he can. This gentleman can put it into the chat. Yeah, that's great. I'll answer it. No problem. Sorry, Bill. You can ask again. Sorry. DNA. Yeah. You know, it's hydrogen bonds are greatly underappreciated. That's my evaluation. But certainly in these minerals, they become absolutely critical to holding them together. You throw away the water, you got nothing. They just fall apart. Did the gentleman have a question?
Do you have, are you aware of retrograde metamorphism concepts associated?
Yeah. Yes, I'm familiar with retrograde metamorphism.
Yeah, I have seen examples of that.
Yep.
That deal with this.
Yep, absolutely. Anything that's what I was making a sort of a point at the beginning, is that everything that we see now will not be there tomorrow. And retrograde metamorphism is basically the cooling and the loss in pressure of a metamorphic rock after it's reached its peak of metamorphism. And so you're looking at effectively a form of alteration, because and perhaps many of you are familiar with garnets that have been replaced by chlorite.
Yes.
So the garnet would have been up to the peak of metamorphism, and as it cooled down and pressure was reduced, chlorite is going to replace that particular. Yes. So that's a good point. It's a form of alteration as well.
Very good. Thank you.
Okay. So I guess I've blown everybody away, and now if they want to eat, that's good. No problem there.
Well, thank you, Andy.
Stop the screen sharing here, right? That was the
Close it.
problem we ran into. Okay, folks. You know, thanks so much for your attendance and participation here in St. Catharines or online via Zoom. You know, we apologize for the technical glitches that we've had. Our plan is to post the recordings shortly. So you'll have an opportunity to enjoy them. And for people that weren't able to get online or attend, they'll be able to see them. You
I
know,
don't think I've signed anything. Have I signed over the rights? I guess I have. Frank is nodding, so yeah, it's probably
yeah,
I did it.
you were drinking last night, so. And so with that, you know, we're going to close the online session. Thanks everyone for joining, and just for the folks here, give us a couple of minutes to set up the lunch, and then you'll be able to go at it. So thanks again, everyone. Thanks, Andy. Thanks, Michael.
That's great.